Hello everyone, here we are for chapter 14. And in this chapter, we're going to learn a wonderful concept that all organic chemists rely on to identify the molecules that they make after a synthesis. Okay, so let's see what is this chapter is all about. Okay, awesome. And it is called NMR spectroscopy, that is called nuclear magnetic resonance spectroscopy. So in this chapter, we will consider NMR, which is nuclear magnetic resonance, which is a form of spectroscopy. That is one of the most powerful tools for the identification of functional groups and for the determination of connections between the atoms in molecules. Okay? So if we are going to identify a substance or a molecule, we need to know how they are connected. So in this technique, we can identify how they are connected. And this is the electromagnetic spectrum. It ranges from cosmic and gamma rays to radio waves. And we are here, visible range 400 to 750 nanometers. And right before visible, we have UV, and then more energy than the visible, and X-rays have even more energy, and gamma rays and cosmic rays carry more energy than any of these. Okay, and then less energy compared to the visible would be infrared. In this region we can talk about infrared spectroscopy in the next chapter. And then we have microwave radiation and radio wave. Radio wave is a milder energy compared to the other ones, milder signal, not the signal, milder energy. And in this area that has radio wave, we study nuclear magnetic resonance spectroscopy. Okay. So what is this nuclear magnetic resonance spectroscopy, NMR? Which is a graph. Normally, if you run a sample of NMR, you're going to get a graph. And this graph shows the characteristic energy absorption frequencies and intensities for a sample in a magnetic field. And that is called a nuclear magnetic resonance spectrum. So in a nuclear magnetic resonance spectrum, we can identify the carbon-carbon and carbon-hydrogen framework of an organic compound. Normally, we can get NMR spectrum with nuclei with an odd number of protons or an odd number of neutrons, or if you have both. Now hydrogen 1 we consider it as a proton, okay, and carbon 13 has how many number of protons? Carbon has 6, and how many number of neutrons? In this one, 7, so it's odd number of neutrons. Nitrogen also has odd number of protons and also neutrons. And fluorine 19 also has odd number of protons. And phosphorus 31, phosphorus also has odd number of protons. So all of these are capable of producing NMR spectrum. Okay, but we are mainly going to concern about a proton NMR spectroscopy and briefly on the carbon spectroscopy. Okay, this is how a typical NMR spectrum look like. You will have axis going from 0 to 8, and then you will see some peaks, and they have different intensities, they have different splitting patterns, and this is a spectrum for ethyl bromide. Okay, and these two that you see over here, they are enlarged, show you how they are being splitted. Okay, so this red one is B here, and then the blue one is there, and we will understand what are these information that we can see from an NMR spectrum. Okay, so A is this hydrogens on the carbon, the blue hydrogens, a signal with 4 peaks. That is A hydrogens, we call it as a quartet. And then the B, a signal with 3 peaks. Okay, we call it as a triplet. And all of these terms are new to you, but don't worry, we're going to learn all of them. Okay. Okay, now the information in more detail. The number of signals in the spectrum tells us how many different sets of protons there are in the molecule. Now, I'm going to refer to the same spectrum I showed you so I can explain you what all this means. Number of signals. So there are 2 signals, A signal and B signal. And that tells us how many different sets of protons there are in the molecule. So there are 2 different sets. The blue hydrogens are different from red hydrogens. So they are 2 different hydrogens. So we have 2 sets. Okay. And this position, why the blue is between 3 and 4, why the red hydrogens are between 1 and 2. The position of the signals in the spectrum along the x-axis tells us about the magnetic environment of each set of protons arising largely from the electron density in their environment. Okay, and the signal where it appears depend on the electron environment, electron density in their environment. Okay, obviously there is 2 hydrogen, there is 3 hydrogens, and these 2 hydrogens, the blue ones are closer to bromine and then the red ones are further away from bromine. So that makes the 2 sets of hydrogen have different electron densities on them. So that is why it causes 2 different signals. Okay. And then the area under the signal. Area under the signal basically also you can consider as the height of the peaks. Area under the signal tells us about how many protons there are in the set being measured. So the B has 3 protons and A has 2 protons. So 3 is bigger than 2. So you can see B peaks are higher compared to the A. And that is the area under the signal. So the height will tell us, give an approximation whether which one has more hydrogens in that signal. Okay. And then you see these multiplicity. I mean these signals are being splitted. They are not just one line. They are splitted further. We call it as the multiplicity, or the splitting pattern of each signal tells us about the number of protons on atoms adjacent to the one whose signal is being measured. Okay. Now let's read it again. The multiplicity or the splitting pattern of each signal tells us about the number of protons on atoms adjacent to the one whose signal is being measured. Okay, so this multiplicity tells us about how many protons are next to the hydrogens that are being interested. For example, so the blue one, there are 2 hydrogens, right? So there are 2 hydrogens on the blue, and these 2 hydrogens are going to split by these 3 red hydrogens. Now this is a signal for the A hydrogen, which is the blue. But there are 3 hydrogens on B. Now when they are splitting, it's always going to split one more than the number of hydrogens on the adjacent atom. We call that as it's going to split N plus 1. N is the number of hydrogens. Okay, now let's see. In your signal A or the A hydrogens, there are 2 hydrogens. These 2 hydrogens are going to split by the 3 hydrogens on B. But it's going to split N plus 1. N is the number of hydrogens, 3. So 3 plus 1, 4. So the blue signal is going to split into 4 little peaks. That's why you see 4 there. And then if you take B signal right there, okay, there are 3 hydrogens on B. Now this B is going to split by the adjacent 2 hydrogens. So 2 plus 1, 3. So the B will split into 3. 2 plus 1, 3, N plus 1. So we call it as a triplet. Okay, so normally you can consider, now you have a spectrum and there are 2 signals in this one. There are 2 different hydrogen sets, blue hydrogens and red hydrogens. If you don't have any other hydrogen in the next carbon, you will simply make 2 signals like that. Now due to the adjacent hydrogens, it's going to split like this. Okay. Now be with me and you'll understand more as we go along. Okay. Now, chemical shift. So what is chemical shift? And we're going to give it the symbol delta. So this is the delta ppm. So on this x-axis you will see the chemical shift recorded as parts per million ppm. Okay, chemical shift is delta. In a typical NMR spectrum, you will see this chemical shift data and also see integration, areas of peaks. Integration, these are the areas of peaks. Also tells us the number of hydrogens. And then also tells us the multiplicity, meaning spin, splitting, and coupling constant. We'll learn about the coupling constant in a bit. Okay, so again, this is how NMR looks like, and then the details that you can get from the NMR. And this at 0, you can see here TMS, and that is the reference compound called the tetramethylsilane. We keep it as 0 so we can have a starting point. We make it to 0 signal, and then you can measure whatever in your sample. So in a typical proton NMR, this is how it is being recorded, and these are the information that we can get from an NMR spectrum. So it will tell us record as proton NMR 300 megahertz. 300 megahertz is the strength of the instrument that we are measuring this proton NMR. And CDCl3 tells us we are using deuterated chloroform as our solvent, because in the solvent, if you have hydrogen, that can also interfere with the hydrogens in the compound. So normally we use a solvent that does not have any hydrogens in it. So this if you have this as CHCl3, that would be chloroform. So hydrogen is being replaced. So this is chloroform, CHCl, chloroform, CHCl3. Now the chloroform hydrogen is replaced with deuterium. So now it doesn't have any hydrogens in it. CDCl3, that's the solvent we use. Okay. So this is how we record a proton NMR spectrum. And the delta tells us the ppm where we are recording our spectrum. Delta .45. So this is our main spectrum and this is the expanded version. So around 3.45 you have 2 hydrogens. You have a signal that tells you that there is 2 hydrogens, and it is a quartet. Quartet means like this, 1, 2, 3, 4. We call it as a quartet. At 3.45 there are 2 hydrogens. It is a quartet. And then the J means the coupling constant. Coupling constant in hertz. And then this quartet triplet that tells us the multiplicity, and J 7.2 Hertz coupling constant. I'll show you coupling constant values in a little bit, so that way you will understand what is the importance of the coupling constant and what information we can get from looking at the different coupling constant values. It's given in units Hertz, and this is for HA hydrogen. HA hydrogen. Okay, so HA hydrogen is in 3.45. It's a 2 hydrogen and it is a quartet. Okay, now with that information, let's see, you are taking this hydrogen spectrum from an NMR machine, and then you are supposed to deduce the structure of this molecule. Let's say you don't know that it is ethyl bromide, but you are only given this information where you have the spectrum. So how do we deduce the structure? So simply we're going to put the pieces together. It's like you're putting a puzzle pieces together. Okay, now we know that there are 2 hydrogens. That's going to be piece like that, 2 hydrogen. And then it is a quartet. You see, it says it's a quartet. Quartet means then the adjacent hydrogen need to have 3 hydrogens. Remember the hydrogen, so these 2 hydrogens will split due to the hydrogens on the next carbon, due to the n+1 rule. So if you have 3 hydrogens on this carbon, then this A carbon will split into a quartet. So you can see that is this quartet. Okay, 2 hydrogens, a quartet. And then if you go to carbon B, there are 3 hydrogens on carbon B. But these 3 hydrogens on carbon B going to split due to the 2 hydrogens on carbon A using n+1 rule. So there are 2 hydrogens on A. So 2 + 1, 3. And that's going to be a triplet. And then you see on the B, carbon B, there are 3 hydrogens on carbon B. And then it is a triplet due to the 2 hydrogens on carbon A, and it's going to split n+1. N is the number of hydrogens on A plus 1. And then we know by looking at this information, in our molecule we have this CH3 CH2 part. Okay, and then we don't know what is the other part. Remember, we have a bromine also. And in order to identify what is next to carbon A, we should be given maybe even the molecular formula or some other information. And one more thing when we can find out is that the carbon, the blue carbons over here, 2 hydrogens on carbon A, is more further downfield, like in this area, 3.45. Okay, so that information tells us it is close to an electron withdrawing group. I'll talk about it in a minute. Okay, but this is enough for this slide, I believe. We can move on. Okay, now the position of the chemical shift. The position of a signal along the axis of an NMR spectrum is called its chemical shift. Okay, so this position where we are finding our signals, we call these as chemical shifts. The chemical shift of each signal gives information about the structural environment of the nuclei producing that signal. Counting the number of signals in a proton NMR spectrum indicates at a first approximation the number of distinct proton environment in a molecule. Now if you count here, there are 2 distinct sets of hydrogens in this molecule. Okay, and these signals appear due to the chemical environment they are in. The spin state of a nucleus is affected by an applied magnetic field. Now, nucleus. So you can consider all of these as nucleus. By itself, it can face in any direction, right? When the molecules are in a container or maybe in a solution, in a liquid, so there are no magnetic field is applied, you can see that they can face in any direction. And then you are applying an external magnetic field, we can consider it as B naught. When the magnetic field is applied, so these random spins, they either align along with the magnetic field, so you can see that this is pointing upwards, and some of these spins will also align along with the magnetic field, and we call it as alpha spin state, and it would be lower in energy. And some of these will align against the applied magnetic field, and we call it as beta spin state, and you can see that they are against the applied magnetic field. Spins are pointing downwards, and they are going to be energy wise, if this is the energy to begin with, aligned ones would have a lower energy, and then opposite ones would have high energy, about the same amount and equal but opposite. Okay. The delta energy between the two spin states depend on the strength of the applied magnetic field, P naught. So this is the energy. So the same thing that we had seen here, that depend on the applied magnetic field. So we have NMR machines that runs at 300 megahertz applied magnetic field, or you can have 600 megahertz. 600 megahertz or 300 megahertz. The 600 is more strength, and then you can see they are splitting it is more. Okay, this is the applied magnetic field in Tesla. So like we saw earlier, the bottom one would be alpha spin state, and then the top line would be beta spin state. All the hydrogens in a compound do not experience the same magnetic field. Okay, now be effective. Is the magnetic field affected by the hydrogens in an environment? So that depend on the applied magnetic field, which is the magnetic field coming from your instrument, and then when you subtract the local magnetic field is the environment that the hydrogen is in the molecule. That depend on the electron density on the hydrogen. Okay, whether it is going to feel more applied field or less applied field, so that will give us be effective. The electron surrounding the nucleus is the B local. Decreases the applied magnetic field sensed by the nucleus. Because we are applying a magnetic field, and our little electrons that are on the hydrogen is also act as a magnet. So there are two magnetic fields. Okay. So where protons show a signal. Let's look at here. So there are two terms that we're going to learn. Remember, this is the zero, and then we have chemical shift in delta. The more further to the left, we call it as down field. More closer to the zero, we call it as up field. Now, how do we get down field? These protons sense a larger effective magnetic field, so come into resonance at a higher frequency. If the hydrogens are feeling more of the applied magnetic field, we call they are de-shielded. They are not shielded by the electrons. They are more open. So they feel more of the applied magnetic field, and they appear at a higher frequency or downfield. And if your hydrogens are shielded by surrounding electrons in the molecule, these protons sense a smaller effective magnetic field, so come into resonance at a lower frequency. We call them as shielded nuclei, and they are upfield, and that is the reason that we have three sets of protons at different peaks like this, because they feel the applied magnetic field differently depending on the electron density around the hydrogen atoms. Okay. Chemically equivalent protons in the same environment. Now this is propyl bromide. Okay. Now if we draw this molecule, we're gonna draw it like this. CH3. And then you have bromine right there. Okay. Now these two hydrogens, we call they are chemically equivalent protons, because if you take this hydrogen right here, this hydrogen is bonded to carbon, and then you have bromine, and then you have an ethyl group, and then this hydrogen, it is bonded to carbon, bromine, and an ethyl group. So they are chemically equivalent. So because of that, both of these two hydrogens, let me label them as A, B, C. A would appear as a one signal because they are in the same environment. Okay, that's a one chemically equivalent set of protons. And if you take B hydrogens, so the B hydrogens, there are two hydrogens. So if you take the top hydrogen, the green one, it is connected to carbon, and that carbon B has C and A attached. If you look at the bottom hydrogen, the green one, that is connected to carbon B, and this also has C and A carbons with their groups attached to it. So both hydrogens are in the same environment. So because of that, those two hydrogens, we call them as chemically equivalent protons. And then you can take C hydrogens. So the C ones, this one, these three. Those three hydrogens are also chemically equivalent because each of them are connected to a carbon that has the same group attached to it. Okay, so in a proton NMR, if you don't look at the coupling constants or coupling of the atoms, you can see there are three chemically different environment signals for this proton NMR spectrum. Okay, so their signals would be 1, 2, 3. And then depending on the number of protons, they will have that height different. So this would be a little bit higher because this is the C, and this is B, and this is A. A and B will have the same height because they have two hydrogens, and then the C would be a little bit taller because there are three hydrogens. So if you are not considering about the splitting, you should be able to see three signals on the proton NMR, and you can consider this as your 0. Okay, and the placement of ABC depend on their electron density on each hydrogen, surrounding each hydrogen. Okay, but I'm just going to explain you about the chemical equivalent protons here, so you got the idea why they are called chemical equivalent. So there are three signals. We should be able to see three from this compound. Now how many signals? The same thing that we looked at in the previous slide. There are three signals here, ABC. A is 3 different hydrogens, B would be different from A and C 2 hydrogens are the same. So there are 3 signals. And how about here? The bromine is attached to the middle carbon. So here, if you look at, this is CH3, this is CH3. Both of these are attached to carbon with hydrogen and a bromine. So that makes this carbon and this carbon are chemically equivalent. So there are, how many signals would you expect for this molecule? 2 signals, because A they are the same and B would be same. So if you draw the NMR spectrum, you will see 2 peaks only, 2 signals, A and B. Okay, and their ratio is going to be 1 to 6. 1 to 6. There are 2 signals for this one. How about the next one? So, ethyl methyl ether over here. Okay, so there are 3 hydrogens. Okay. So 3 hydrogens over here attached to a carbon that has oxygen. That's a different environment. And then these 2 hydrogens on C next to oxygen as well as carbon. So C going to be different than the B carbons, and A hydrogens are going to be different than the C. So there are 1, 2, 3 signals. And on the next one, dimethyl ether, you can see these 3 hydrogens on this carbon, these 3 hydrogens on this carbon, both are connected to oxygen. So you can see these 6 hydrogens are in the same chemical environment. So there's going to be 1 signal. So likewise, we can look at each one separately and see if these number of signals make sense. So now this one, 3 hydrogens on carbon attached to oxygen, 1 signal. And these 3. So they are all attached to carbon next to oxygen. So there's going to be 1, 2, 3. All these hydrogens will end up being as a 1 signal or 1 area. So that gives you 2 signals, this and this. Excuse me. And then this one again, there is 3 hydrogen on the carbon next to oxygen, then 1 hydrogen carbon that is connected to oxygen and chlorine. So these A hydrogens are going to be different from B hydrogen, so 2 signals. And then in this molecule you have an alkene, and these 2 hydrogens would be same and these 6 hydrogen would be same, so 2 signals. This is again a symmetrical molecule, this hydrogen and this hydrogen in the same environment, so it's 1 signal. And this is benzene, again all hydrogens are equivalent chemically, 1 signal. And now here you have here NO2, electron withdrawing group, that also makes this molecule symmetrical, but A and C are not going to be the same because these 2 hydrogens are closer to NO2, these are further away. So these 2 will have the same chemical shift, these 2 will have same chemical shift, and this would have a different chemical shift. So there are 1, 2, 3 signals for this one. Each set of chemical equivalent protons gives a signal in the proton NMR spectrum. Okay, now in this molecule, how many signals? Now, bromine is attached to this carbon. Now in this case, A and B are not going to be same. They are not going to be equivalent. So then, molecule is not symmetrical. It will make 3 signals. Same on this one. Since you have chlorine, that will give you 5 different signals. H, A and B are not the same, equivalent, and C and D are not equivalent either. But D here and D here, they are going to be same, and C going to be same, and these two are going to be different. That gives us total 5 signals. I think this is enough for this section, and we'll start the next session in a new video.